my cars kind of stayed the same at like 123, but then my chem phys and then my bio went up.
Nice.
So I don't know, I was kind of happy with that.
That's
And
good.
then yeah.
Awesome.
So I had a question on the schedule. So there's no I shouldn't take an exam this
Oh,
Friday.
I just have that down for like when I first made the template. So,
Mm-hmm.
it's just to like block it out for like Thanksgiving. But if you feel like you can work on those days, then you can just continue uh what you're up to, which I think
Okay, well,
yeah.
I was thinking of taking the third party full length six on that day, Friday, and just
Gotcha.
kind of continue with the U World. And then this will kind of be maybe seven.
Mm-hmm.
Okay. All right, cool. All right. I wanted to go over some of the one of the Altius questions I kind of struggled on.
Oh, okay. So how do you how do you approach
I don't really know like the concept for this, like saying two
magnetism?
wires with opposing current. Yeah.
Got it. So let's talk about this. So, do you remember like your right hand rule?
Uh, Not really. I forgot it.
Okay. So draw. This is one wire, and this is the other wire. And- Okay. So the right hand rule, there's two of them. One of them is when you have your hand like a karate chop, and your your thumb is pointing. So like, yeah. So if it's a moving charged particle, it'll create a magnetic field as well as a force. So let's say it's a thumb. Okay, let me start with, let's say we have a positively charged particle moving to the right, and we have a magnetic field. So X is if it's going into the page.
Hmm.
And let's say we want to figure out the force, the magnetic force that this charged particle experiences. So what I'm going to do is the direction it's traveling, I'm going to have that be my thumb. So it's going to the right. So my thumb is going to the right. The magnetic field is going into the page. So these fingers should be pointing in the direction of the magnetic field. So that's going to go into the page, and your palm is going to be the direction of the magnetic force. So the magnetic force in this is going to be going up. Okay.
That's your palm, the middle one right here.
So, yeah, palm is facing up, which is the
Okay.
direction of the magnetic force. So that's one version of this. The other version of this is more so of a curl type of thing, meaning if we had, you know, a wire, just one wire actually here, and let's say that the current is going in this direction upwards, what we do is we have our thumb then point in the direction of the current going up, and that's where you do the curl. So on the right-hand side, the magnetic field, which are, the direction of my other fingers, goes into the page, and then it curls as you go into the page, it curls until it, rotates, and then it comes back on the left side out of the page. And that can be the dots, right?
Mm-hmm.
So, okay. So let me ask you this. So let's say we have, so the dots means it's a magnetic field coming out of the page. And let's say that we have this charged particle moving down.
That means your hand is on the other, like it's flipped.
So just use
Since
the
you're
right hand rule. So basically your thumb is going to be the direction of the charged particle, like the direction that it's traveling.
so like that down.
Uh-huh. Yep. And then your other fingers are going to be the direction of the magnetic field, which in this case is coming out of the page.
So
So,
like what?
the magnetic field is pointed out of the page. So you're going to have your other fingers go towards you.
Like that?
Uh-huh. But
Okay.
just remember that the thumb would be on the bottom.
Yeah. So
Yeah.
like that.
Yeah.
Okay.
So now what direction is your palm facing?
That with the my right.
Um, did you say right or your left? Wait. Sorry.
Or yeah, my right.
Oh,
Or
so if it's coming out of the page, your thumb, I mean your palm, you're saying it's to the right? I don't know if that's due to zoom or whatever, but it should be. So if your fingers are pointed towards you and your thumb is pointing down, your palm should be facing to the left.
I don't know. It's face, I don't know. It's to my right, the palm. So I'll
Uh-huh.
say it's my left, it's my right,
Uh-huh.
and the thing is going down
So
in my
wait.
palm.
Your these fingers are pointed in the direction of the field, and the field is coming out of the screen, pointing towards you.
Or it's like this.
Yes.
Okay. Now then, oh, okay. I got it. Yeah, so
So
it's
that's
to my left.
to your left, you said?
Yeah.
Yep. So that would be the direction of the force, right?
Hmm.
Okay. So now I'm going to make these the two wires, and one of them current goes that way, the other one current goes that way. So now let's use that right hand rule to, let's start with the one on the right. Um, so your thumb is going up, and then this is when you do the curl. So on the right hand side, should the magnetic field be into the page or out of the page?
Wait, which one? The fingers are the magnetic?
Oh yeah, so it'll still be like these fingers pointing in the magnetic direction, but this time you're going to do a curl. So for instance, this over this example,
Mm-hmm.
So you see that my thumb, this could be like your thumb, and then this could be like the rest of your fingers going into the page or into the screen on the right side.
Mm-hmm.
And then by the time it wraps around the wire on the left side, it should be coming out of the page,
Out of the
right?
page. Yeah.
Good. So we're going to do this. So for the wire on the right, I'm going to use blue to write down the magnetic field direction. So try this. So this one going up. So that means that on the right side, like tell me about the magnetic field directions.
So it starts out going into the page, like, and then goes out.
Okay. So into the page on this side,
Yeah.
and
And
then
then on the left side, it's going out of the page.
good. So I'm making blue the color of the magnetic field produced by the current by the wire on the right. Now I'm going to use green for the wire on the left. So now for that one, our thumb is going to be pointing down, right?
Yeah.
And then it would go, yeah, then tell me what it
Out
would.
of the page,
All right, on what side of the wire, left or right?
the left.
Left? Are you saying, are you sure about the
Oh,
out?
wait. Let me do it again. So it'd be going out on the right.
So that's for the magnetic force, but you're thinking of this,
Yeah.
but we're gonna do this, the right hand rule where you
Okay.
curl.
Okay.
So for this, if the current is going down, do the curl. So it goes like into the page or out of the page.
Into the page.
Okay. And that's on the left side or the right side of this wire.
I think the left side.
Okay. And then it should be wrapping around and then coming out of the page on the right side, right?
Yeah.
Okay. All right. So now that we have the magnetic field, right? Because the thing is, when we're doing this to find the magnetic force, we need both the direction that the charged particle is traveling or the current is traveling, as well as the magnetic field, right?
Mm-hmm.
So this version of the right-hand rule lets you figure out what the magnetic field is.
Okay.
So now we can use this one. Okay.
Yeah.
So let's start with the wire on the left. Now do the right-hand rule with the force for that one.
So then it's going down.
So you could think about it like this. So if it's coming like out of the page there, we can have it so let's see. I'm trying to get an image of this.
The force is down, right? All right. This is
So
current.
the thing is that the wire on the right produces the magnetic field coming out of the page everywhere to the left of it, like including, and then for the wire on the left in green, when it comes,
Hmm.
out of the page here, it's going to cause that to go out of the page over there.
Okay.
So that means that this wire here experiences, due to the other wire, a magnetic field that is coming out of the page. Okay.
Hmm.
And so if you use the right-hand rule to find the force, what would that be? The force that wire one experiences.
We're gonna be going this way.
Yep. Now do it for the wire on the right.
Uh, I'm gonna be going to this way
Which
or
one?
this way. I don't know. I have it to the right. Does the palm have to face out?
Oh yeah, so now the thumb is pointing up and the magnetic field from the wire on the left that's coming out of the page comes out towards us. And so, yeah, it'll be to the right.
Okay.
So these forces would repel, right?
Yeah.
Yep.
Okay.
So, so yeah, so for these choices, they're saying,
So if the current was sorry, if the current was both up, they would attract each other.
yep,
And if they were both down, they would also attract each other.
yep.
Okay.
Hmm.
Okay.
Yeah. So for these choices, it says the force created by the magnetic fields will be zero. Force created by the magnetic fields will be at a maximum. And then if they'll attract or repel one another. Um, so yeah. So the force will
Okay.
not, yeah.
That makes sense.
Mhm.
All right. Uh, I still had a question on this genetics, like Punnett squares type questions. I kind of tend to struggle with these. Um, I think you're just talking about experiment one.
Mhm.
It says approximately what fraction of the F2 generation is expected to die? Kind of strong with like F1, F2, and then how do we create the Punnett square? So like experiment one's right here.
Okay, so yeah, for dihybrid crosses, which can be kind of annoying, I like to just separate them into two Punnett squares. So I'm going to do one for the E's. And then for the P's, okay, like that. And so these are going to be that F1 generation. Like you'll have big E, little e, followed by big P, little p, as well as big E. So like your genotypes would be like E, lowercase e, big P, big E, little p. Or you could have little e, big P, or little e, little p, right?
Okay.
So these are the F1 generation, and they said that they picked the ones with this genotype to cross to make the F2 generation, right? So that's
Yeah.
big E, big P, little p crossed with the same thing. And then I would do another thing where I write out the two Punnett squares. Big E, big E,
So
little
they just cross these together?
uh-huh,
Okay. All right.
E, little E, and then big P, big P, little p, so big big P, little p, uh, big P, little p, little p. So the genotypes now would be big E, big P, little p. You could also have big E, little p. You could also have little.
Don't you mean big E, little e, or
Oh no, I'm just writing out all of the uh possible gene.
uh okay.
Yeah, like basically like what I'm doing is big E, big P, little p, and then big E, uh, little p, right?
Did you do that here or no?
Yeah. For
In
so
the F1?
yeah, so here, let me show you. So for this cross, right? I just wrote them into separate Punnett squares.
Yeah, I understand
And
that.
then yeah, so I have big E, little e, and then I can make one with big P, little p, as well as little p. And that's what you see here, right?
Oh, okay, okay.
And then the little e with the big P, little p, and then
Mm-hmm.
little e with little p gives you these.
Okay.
And then,
So you don't look at the ones at the bottom?
oh no, I do. It's just that there's out of this entire thing, there's only two. There's big P, and there's little p.
Oh, okay.
And out of here, there's only two as well. There's big E, little e, and there's little e.
Okay.
So now I combine big E with both of these, and then little e with both of these as well.
Okay.
So this is just like my preferred way of doing these dihybrid crosses because making this type of
Yeah.
4 by 4 is a lot. So okay, now where was I here? So big E, little big P, big E, little p. Then we can have big E, little e, big P, big E, little p, and then little e, big P, big little p. Um, oh wait, what's that? Sorry, this one is big P, big P. Let's get that. Okay, so big P, little p, big P, little p, big P, big P, big P, little p, um, big P, whoops, little p, and then little p, little p. So the genotypes I have here is big E, big P, oops, big P, big
Mhm.
E, big P, little p, damn it, big P, little p, big E, little p, and then big E, little e, same thing, big E, little e, big P, little p, big E, little e, little p. And now I'll do it for the lowercase e's. So little e, big P, little e, big P, little e, little e, little p. All right.
Okay.
So that gives me, so that's basic. So basically, um, this is the F1 generation.
Yeah.
This is the F2 generation, right?
Yeah.
So, okay, for the F2 generation, they said that flies with two big E, as well as ones that had the mutant. So this and this, these ones don't survive past the larval stage, right?
Yeah.
Meaning, so anything with the biggies are gone. So these are gone. And then if you have little e, sorry, big E, big P, that's also gone. So big E, big P, or big P, but I already crossed those out because of the EE. And okay, what fraction? Um, okay, what fraction? Let's see. Two mutant ENA alleles, big E, two mutant PTP alleles, and at least one mutant ENA allele did not survive past the larval stage. What fraction is approximate to die during the larval stage? We have the oh, I forgot to cross some of these out. So wait, Sorry, let's see. Big E, big E, big P, big P, big E, big E, big little P. Oh, you know what? Okay. So there's multiple versions of this F21. So here, I'm gonna take that. I'm gonna just throw it here so I have room to do it again. So I'm gonna have to do it for each of these, meaning that we have big P, one of them. Then the
Mhm.
big E, little e, we have two. So big E, little e, um, big P, big E, little e. Uh, big E, big E, big P, only one of those. And then it'll be big E, little e, cross with big P. Or I should include all of the ones with big E. Okay, there's two of these. And then there's little p. And I think there's one of those. And then we have big E, little e with big P. And we have two of these. And then we have big
We
E.
have two of those.
Yeah. What
I
I
only
was
see
thinking.
one.
Oh, yeah. So big E, little e, big P is one. And then this
Yeah.
one is the second big E, little e.
Oh, I was
Little
looking
e.
at a big P. Okay.
Yeah. So it's like a distributive property kind of thing,
Yeah, yeah.
right? So two big P's.
Mhm.
And then we have big E, little e with the big P, little p.
Mhm.
And that's only one. And then the last one would be big E, big E, big E, little p. So this comes out to one, two, three, four, five, six, seven, eight of them. Um,
Did you count the two little E's?
Two little e's. Well, those ones will survive,
Okay.
but I think sorry, I think what I did here was let's see, big E, big E, big P, little p is here and here. So there's two of those as well. And then big E, big P, little p. Oh, sorry. Yeah, there's two of those. And then big E, little p is two of those as well. So, but all in all, I think this comes down to like one, 2, 3, 4, 5, 6. So 6 out of the total, which would be 16 or 16, which would give you the 3/8. So
Okay.
yeah, sorry. That was a lot more complicated than I had intended. But what you're essentially doing is you're doing like a distributive property kind of thing.
Mhm.
Here, I'll show you what I mean to make it more clear. So if we had first, I would do this. Gives me big E, big E, big E, little e, big E, little e, little e, little e, and then this one, big P, big P, big P, little p, big P, little p, and then little p, little p. So I'll use blue. I'm gonna do this, big E, and I'm gonna distribute it to the big P, followed by the big P, little p. So next one is big E, big P, little p, followed by
Yeah.
the third one here, which is another big E, big P, little p. And then lastly, that one, big
Mhm.
E, little p, little p. So you see what I mean by I'm distributing?
So you're only doing the top one, not the like the other ones, because it's like kind of the same.
Oh, no, no. So this is just for, so these are all of the genotypes that have big E, big E.
Yeah.
Okay, so now I'll use green for this one. So big E, little e. I'm going to distribute that to the big P, right? And then I'm going to distribute it to the big P, little p. So big E, big P, little p. Then I'll distribute it to the other big P, little p. And then lastly, little p, little p. So now that these are the genotypes for that. And then in pink, I'll do this one. And this one is the same as it's another big E, little e one, but it counts as additional genotypes. So again, it's just the same thing as above. Yeah, like that.
Mm,
And then lastly, I'll use orange for this one. Little e, little e. I'm going to distribute it to the big P, and then to the, so little e, big P, little p. Another one. So little e, big P, big, little p. And then little e, little p.
okay.
And that gives you all 16 genotypes, right?
Yeah, this
And,
this part I get. I understand this so far, but then
yep.
like what's F1 and F2 and then like
Yeah. So F1 is that basically this. This is F1 that they give us. So when we cross the F1, these are all 16 possible genotypes.
okay.
And so what they said in the passage was anything with a big E, like big E, will not make it past the larval stage. So that rules
Yeah.
out these guys.
Okay.
And then they said if you have a big E, little e with a big P, that that will also not survive. Um, so big E, little e with a big P, these two, right?
Yeah.
And I think that was the only one that they said. Or maybe they said
Yeah.
one, two, three, four, five, six. Yep. So now you see that six of these out of the 16 are the ones that don't survive.
Yeah.
Hmm.
This way kind of cleared it up because this one you were like breaking it up and then distributing. This kind of makes it once you
Yeah,
do the whole dihybrid cross kind of makes sense. Okay.
yeah.
Yeah.
But yeah,
I was
dihybrid.
just getting lost in the dealing. Yeah.
Yeah. Because here I was just writing the different possibilities, but I didn't put down one for each genotype. Like for instance,
Yeah.
like that's why we have like these two are the same, these two are the same, these two are the same, right? But they still count.
Hmm.
So, yep.
Cool. I had another question on this passage, I think.
Okay, suppose a male heterozygous for big E, big P, little p, mated with a male of an unknown genotype from experiment one. Um, and F1 of an unknown genotype from experiment one. Um, so I erased it, but what were the so that
I kind of have it. Wait, what are you looking for?
I could
The
okay.
okay.
So the F1 male. Oh wait, F1 males. These are the options. So I'll just write this again. So big E, little e, um, big P, little p, big E, little e, little p, little e, big P, little e, little p. So this one over here, F1 generation.
Yeah.
Okay, so I should have just typed it out. Okay, these are the possible F1, and
Yeah.
we're crossing big E, big P, little p with something from F1, one of these. So now they're saying that when they made the F2 progeny, that 25% died in the larval stage, meaning, it'll have either two big E's, or two big P's, basically. Those ones will die. So,
Mhm.
okay. So let's think. If it was this, so I guess I can do, let's see. So only 25%. Okay, so if I cross this with these possible values here, let's see. Okay, for this one, Let's see. Okay, if we had big P and little p, you would get big P, um, little p, big little p, and we know that, okay, maybe that can work. That actually can work. Okay, so the p's like that work. But let's say that we had big p, and big P, we get big P, big P, little p. And we know that if you have big P, you're not going to survive. So these would die off here.
Yeah.
And now for the other one, it's whenever it's big E, big E. So if we had big E, little e, big E, little e, kind of same. Oh, so okay. Big E, big E over there should not survive. And actually, that makes sense for the fact that they said that 25% died. Because from here, 25% the ones with the big P's die. And then here, the one with the two big E's die.
Yeah.
So that would be the 25% of that F2 progeny.
Yeah.
So, yep, should
Well,
be.
what would the genotype be? So how'd you get to this? Because aren't these uh
Oh, yeah. So these are the possible like genotypes here. And so
yeah,
first I crossed big E, like one of these to get this. And then I crossed, because out of these possible phenotypes, two of them have big E, little e, and then two of them have little e, little e. So if I did that, if I did big E with little e, I would have half of them, or rather, all of these should survive, right? Because
yeah.
only if you have big E that it won't survive, right? So
Mhm.
that rules out the phenotypes that have little e. Okay.
Okay.
And then for the P's, right? I did big P. Well, okay. So here I put big P. Hold on. Big P, and then little p is what I have there. And this means that there's no big P, so these will all survive, right?
Yeah.
Here I did big P crossed with big P, and we get one that's big P. It kind of look like it's little, it could be confusing because the P, like the big P and the little p look the same. So
Okay. So you cross big P, little p, and then big P, little p.
yes,
Okay.
and that gets you big P. And we know from the passage, if you have big E, or big P, you'll die.
Yeah.
So it can't be the ones with little p's, because those won't create any big P,
Mhm.
right? So the only one that's left is this one. Oh no, wait. Big P. Oops. Yeah, the only one that's left would be that one over here.
Okay.
Mhm. Yeah, and in this pedigree here, they're showing us the possible male genotypes. So yeah, those are the ones that I wrote out here. And yeah, you just want one where, let's scroll down some more. Let's see. Okay, so only 25% die. Yeah, so they're saying that these die. So basically, if you have, wait, flies with these die as larvae. So anything with the big E's is going to die. And then anything with a big P is going to die. Or rather, big E will
Yeah.
die and big B will die. So the four possible
Okay.
phenotypes, yeah.
All right. Okay. That makes sense.
Yeah, these can be quite tough.
Yeah. I don't like those type of questions.
Yeah, I mean, either.
Okay. I think this is like a reaction problem or just I don't know.
Researchers want to synthesize valine from isovaleric acid, the enol shown below, with certain carbon atoms labeled, is formed from the reaction of isovaleric acid with PBr3. Um, okay. Um, does PBr3 like ring a bell?
It was on a flashcard. It was like, is it like SN2 or something?
So it's a way that you can convert an alcohol into an alkyl halide,
Yeah.
similar to SOCl2. But yeah, it is through an SN2 reaction. So, um, let's see. The enol is shown below, and let's see if Br. Oh wait. Oh, sorry. This is what forms. Okay, this is what forms as the product when you use PBr3. So that's the bromine that got added. Um, okay. So if Br2 and water are added, which of the following will be brominated in the final product? Um, okay. So we're gonna have, so let's see. Um, the bro the bromine is going to, let's see. Okay. So from over the enol, a bromine will be taken. Um, okay, so what we're gonna have happen is the electrons from this hydroxyl group will go here to produce a double bond there, where the this is going, oops, this double bond is going to go there, or rather. if we have the bromine, this can take one of the bromines and, this can break off, and that can give you the bromine being added here. So yeah, so the molecule you'll get next is going to be that. Basically, you're brominating your alpha carbon, which is that one.
Okay. Uh, so would it be three?
So three
Oh, because
already
this is the
have
product.
Toyota.
Because it's the product. This is the product.
This is the product of isovaleric acid with PBr3,
Okay.
but when you take this product, which is the enol product, and you add bromine and water, it causes another bromination, and this is the mechanism for that. And so you should
Hmm.
be left with this. Oh yeah, here we go. So we have our acyl bromide enol form, and you can see that the lone pairs from the hydroxyl can go here, and then lone pairs from the double bond can go here to give it a negative charge there and a positively charged OH group here. And then that negatively charged one can just take one of the bromines from bromine, and you can see that the bromine gets added on that second carbon.
Yeah.
And then the leftover bromine can deprotonate the OH group to give us our acyl bromide. Um, and then if you want, you can turn it into a bromo acid by adding water and hydrolysis, um, causing hydrolysis to cause this bromine to break apart and turn into HBr to get this as your final product. But yeah, if you scroll down more, so it says reactions at the alpha position of carboxylic acids are an extremely important class of reactions in organic chemistry and biochemistry. Substitution of bromine on the alpha carbon of a carboxylic acid begins with the addition of PBr3, converts it into an acyl bromide that can tautomerize to the enol form, and then when the Br2 is added, the alpha carbon of the enol acts as a nucleophile and attacks the bromine. Um, and yeah, it takes one of the bromines.
Okay.
Yep.
Yeah. Makes
So
sense.
yeah, so this is a good topic to know about.
Mhm. I was wondering if I kind of liked how we went over the section bank,
Mhm.
like kind of just breaking down a passage and stuff.
Yep.
So, wonder if we can do like a little bit more of those.
Yep. We can do that.
This time for Chem Phys.
Okay.
Okay. Okay. The human eye forms clear images because the eye lens of diameter 1 centimeter is transparent and focuses the light onto the retina at the back of the eye. Okay. An opaque eye lens can be surgically replaced with an implant lens First, the opaque lens is emulsified through the application of ultrasound waves. The ultrasound wave frequency is chosen such that the ultrasound wavelength equals 1 over 200 of the diameter of the eye lens. Then the lens is aspirated and an accommodating intraocular lens is implanted in the support structure of the removed eye lens.
All right, let's talk about this so far. So, human eye forms clear images because the eye lens of diameter 1 centimeter is transparent and focuses the light onto the retina at the back of the eye. Um, so they'll probably ask you something about uh optics related to corrective lenses, right?
Yeah,
Okay. Because you want to look out for those buzzwords. And then an opaque eye lens can be, what's opaque mean?
like clear or
Mm, so it's the opposite of clear, meaning you
like
can't.
when there's white stuff,
What's up?
can't see. I
Yeah,
don't know.
yeah.
Yeah.
It'll cover it completely, so you can't see it.
Okay.
And then they said that yeah, opaque eye lens can be replaced with an implant lens. So first they emulsify the opaque lens by applying ultrasound waves. What's ultrasound wave mean?
Um, ultrasound.
Yep. What does ultra mean?
Oh, is it talking about like the longitudinal waves or the sound waves?
Well, sound
The
is a longitudinal wave, but so do you remember I don't know if we talked about this, but the word ultra or the prefix ultra. So
no.
in the visible spectrum of light, it's
Oh yeah. I know. Yeah. Bro. So violet is the lowest wavelength, and then red is the highest wavelength.
sure, sure. But I just mean that what's so this is visible light. What's to the left of visible light?
Those gamma rays, X-rays, UV. So there is. Hold on. What's to the left of what?
Um, so first left to right, if we go left to right, what happens to
I know it right to left from like low. So isn't it goes gamma rays, X-rays, UV,
so
visible.
so would those be to the left of the visible light or right?
Those would be to the right.
Okay,
Invisible would be to the left.
okay. So this one is infrared.
Yeah.
So that's because the prefix infra means less than.
Okay.
And you can see that infrared is just less energy than red. Now, what should be on this side, on the right?
The visible.
So this is all visible.
Okay. UV, right? Then
Exactly, right? Because ultra means more than.
yeah.
So that's why it's ultra more than violet.
So this has more energy. This one has less energy.
Correct,
More
correct,
energy slash frequency.
correct. Yep.
Okay.
So now ultrasound. The ultra means more than. So what can that mean in this for ultrasound?
Has a lot of frequency, a lot of energy.
So yeah, so it could be thought of as sound that is above like the frequency that humans can detect.
Yeah.
So good. Okay, continue.
The accommodating lens is a biconvex
Oh, oh,
converging lens.
sorry. So okay, I guess over here. So the USW, the ultrasound wave frequency is chosen such that its wavelength is 1/200th of the diameter of the eye lens. So, they might ask us to do some math for that, right?
Yeah.
I can imagine them saying like, okay, what type of light, would, or actually it's sound, but okay. And then they said the lens is aspirated and an accommodating intraocular lens is implanted in the support structure of the removed eye lens. And yeah, I think this is like for like cataracts or something when, there's
Mhm.
cloudy eyes. So, all right, good. Continue.
The AIOL is a biconvex converging lens with a focal length of 3 centimeters. So they might ask me something about like the thin lens equation
Yeah,
or
very
something.
good, very good.
The AIOL moves away from the retina by as much as 5 millimeter due to the contraction of the focusing muscles of the eye. So
Yep.
I'm guessing it's like they're gonna draw out a like a converging lens. It's saying moves away from the retina.
Uh-huh.
So
Yep, that
ask me
could
a
be like,
question about that.
yeah, that could be like maybe image distance or something, but good.
Yeah. This allows the patient to see clearly objects located nearby. When the focusing muscles are fully relaxed, the patient with an IOL implant can see clearly objects located at large distances. Okay. The AIOL must maintain its volume with a plus or minus 0.020% when its temperature changes by plus or minus 2 degrees Celsius and must allow as much light as possible to pass through it.
Okay.
Okay, okay. Relevant thermal and optical parameters for SiO2s based polymers used in the manufacturing of implant lenses are listed in table 1. Okay, so it's given us the index of refraction, coefficients.
Yep.
So
So we
yeah.
have coefficient of thermal expansion seems to go up as we go through the. Oh, so thermal linear expansion coefficient, attenuation coefficient, and refractive index. So as we go from polymer 1 through 4, we see that the coefficient of thermal expansion increases. We see a decrease in the attenuation coefficient, and pretty much exactly the same indices of refraction.
Yeah.
Okay.
Okay. So first questions talks about what is the distance of between the AIOL and the retina when the patient can clearly see an object located at infinity.
All right. This is
Okay.
you predicted.
So it has to do with like the thin lens equation.
Mm-hmm.
So it's 1 over focal length equals 1 over image distance plus 1 over object distance. So it says when the patient can clearly see an object located at infinity. So over here we have a focal length of 3 centimeters.
Yeah.
I think and then it's given our options are in centimeters, so that's good. So it'll be 1 over 3. And then it says the AIOL moves away from the retina by as much as 5 millimeters.
Okay. So where you
So I have the 1 over, so I wrote out the formula and then I have 1/3 centimeters.
okay.
And then it equals, so is the 5 millimeters the image distance?
So we're trying to find um that image distance
Okay.
because so we have object distance, right?
Yeah.
And we have focal length, right?
Hmm.
So we can find yeah, image distance.
Okay. So 1/3 centimeters equals 1/I plus 1/, we have to convert this to centimeters. So,
Well, so wait, what are you using?
the thin lens equation.
Yep. But why are you using the 5 millimeters?
Thought it was the object distance.
Well, I thought they said the object distance was infinity.
Oh yeah.
So you have your focal length, you have your object distance, so you need to solve for the image distance, right?
But how would I do that if it's infinity? Would it just be three?
Kind of. We're close. What 1/infinity is kind of like what? Equal to
1/, like a million?
so if that denominator gets larger, the overall number gets smaller.
Smaller.
And so the overall number could be close to like what?
Zero? Okay. So it'd be like one.
So put that in your equation.
Okay. So 1/3 plus 1/. So it would just kind of cross out, or like it wouldn't exist, kind of. So it'd just be 1/3 equals 1/I, and then I would be equal to 3 centimeters.
Mhm.
So
So
this would be our answer.
yeah. So now let me talk about why we're not using the 5 millimeters, right? So they're
Yeah.
talking about that is something that when the focusing muscles of your eye contract,
Hmm.
and that causes the AIOL to move away from the retina by as much as 5 millimeters. Okay. And so that's when it's doing something called accommodation, right? But that's what happens when, you're trying to focus or something, but they're already seeing that or saying that the patient can clearly see the object. So basically, like, okay, so like how so like me, I don't know about you, but a lot of people wear glasses and that corrects for an eyeball that's either too long or too short. But most older people, when they get older, they need to get glasses, and they don't need it to be prescription like I would. So like most people like who aren't like really old are nearsighted, which means that we need um something with like a negative focal length, a diverging lens. But for older people, and if you go to like a CVS or a Dwayne Reed or any of those like, like pharmacies or whatever, they have a bunch
Mm.
of glasses, and if you
Yeah.
look at them and you can see the prescription, it's going to be positive, which means that it's a convex lens, but that also means that because what happens as someone gets older is that there's something called the ciliary muscles that cause something called accommodation. If you're looking at something close by, the ciliary muscles will either contract or relax to make it so that you can see something close. But if you look at that, then at something far, your ciliary muscles will either contract or relax so you can see that thing that's far away. And we all can do it, but as people get older, since it's based on a muscle, the muscle weakens, and that's why they
Okay.
could use something like that. Yeah.
Yeah. Okay. Yeah, that makes sense. So if it's negative, like you said, when we go to the store, it would be like so it said convex for positive,
Yep.
so it would be like concave for negative, or
Yep. Yep. So basically, if your eyeball is okay, we want the light rays to converge on the retina here, right?
yeah.
Now, if your eyeball is longer than average, the light rays will converge in front of the retina. So, how do we fix this? Well, we can use a diverging lens, which causes the light rays to diverge a bit before they hit the cornea, and it kind of delays that convergence. So when it does converge, it'll converge on the retina.
Okay.
Opposite is true if you are farsighted. If you're farsighted, your eyeball is shorter, which means that the light rays converge behind the retina. So for them, you want the light rays to converge sooner. So you would use a convex converging lens. So it converges sooner.
Okay.
So those are they like to test optics, like thin lens equation kind of, or yeah, optics in the context of corrective lenses like that. Yeah.
Okay. So this part right here is for like nearsightedness.
Oh, for the opposite, for farsightedness.
Oh, for farsightedness. Okay.
Yeah. Do you wear
Uh,
glasses or anything?
yeah, I have them right here. It depends on how I'm feeling on the day.
Um,
Yeah.
are you're nearsighted?
I'm farsighted.
Really? So your
Yeah.
prescription is a positive value, right?
Yeah.
And if you feel the lens of your glasses, like as you go towards the center, does it get thicker or thinner?
Thicker.
Yep.
Yeah.
That's a convex lens because a convex is thicker, at the center part, right?
Oh, okay, okay. Yeah, yeah,
So
yeah.
for you, so your eyeball is the average eyeball length is 2 centimeters. So your eyeball length is smaller than that.
Oh, okay.
So normally light will converge behind your retina. So you want a converging lens so it converges sooner to be on your retina.
Mm,
But
okay,
yeah, that's
that's
why you have
interesting.
a positive it's like what's a number? Positive what?
Uh,
Maybe like positive 2 point something, or maybe it doesn't tell you, but
yeah, something around there.
yeah.
You
So
know.
that's it measured in something called diopters,
Yeah.
which is power in when it comes to optics is the inverse of the focal length. Um,
Wait,
yeah.
what's this you said? That's the formula?
Oh yeah. So this is for the power of the lens, and this is in meters. So,
Okay.
so like for my glasses, my prescription is negative 2.75. Negative means that it's diverging because I'm nearsighted.
Hmm.
And the negative 2.75 is in some unit called diopters, which is basically the inverse of the focal length in meters, though.
Okay.
Yep.
Interesting. Cool.
Yep. Yep. Yep.
Oh, shit.
Yeah, it always helps to like be able to make connections with things.
Visualization. Yeah.
Yeah, and also connecting things to your regular life. Because I know a lot of people are like, okay, why do I need to learn optics? Or why do I need to learn this, if I want to be a doctor? But I think it's good to have the mindset of, constantly learning. Um,
Yeah. Yeah. Hmm.
so okay, let's see this one.
What is the nearest location of an object that can be seen clearly by a patient wearing the IOL described in the passage?
Yeah. What are your thoughts here?
I think it's talking about this part right here.
Okay.
Um, Says what is the nearest location of an object that can be seen clearly? Um, I feel like we have to still use the fifth in lens equation
Uh-huh.
using the focal length of this,
Okay.
and that's the image. Uh,
So this time we're going to use the 5 millimeter value, but not on its own. And the reason is they're asking what's the nearest location of an object that can be seen clearly by the person wearing this thing. So we know that um, when so when the muscle contracts, it lets the person see things nearby, right?
yeah.
But when it's relaxed, it can see things at large distances.
Hmm.
So if we want to find out what's the closest object that can be seen clearly by the person, right?
Want
We
it to be contract?
you oh, and then contraction means it's moving away from the retina, right?
Yeah.
So yeah, if you want to see something near, or yeah, the nearest object, you can then put that in for um let's see. Okay. So so in general here, it's like this distance we can consider the image distance, right?
Hmm.
And it can, during the contraction, it can move away from the retina by as much as 5 millimeters, right? So whatever this distance is, we can add the 5 millimeters to that, right?
Okay.
So this image distance, we can add to it the 5 millimeters. And since we are starting off with our distance between here, aka the focal length of 3 centimeters,
Hmm.
this new value here will be 3 centimeters plus 5 millimeters, right?
Hmm.
So I could say the image distance is going to be 3 centimeters. So 3 centimeters plus 5 millimeters is going to be 3.5 centimeters, right?
Yeah.
Okay.
So
And
then we just plug that back in the formula.
yep.
Okay. So we 1/3.
So yeah, how's it going?
Still. So would it be like 21?
Exactly.
Okay. So I guess this is where I kind of got stuck on the I plus.
Mm-hmm. Yeah, yeah.
So you add it on, yeah. Okay. Okay. Which polymer listed in table 1 is best suited for the fabrication of an IIOL? So, fabrication.
Okay. So when making the AOL thing, it has to maintain its volume within plus or minus 0.02% when its temperature changes by plus or minus 2 degrees Celsius, right?
Yeah.
So,
So right here is changing. Let's maintain its volume by plus or minus 2%.
mhm.
So from here to here, it's not that.
see. Um, so so we could take so the coefficient of thermal expansion has units of what?
10 to the negative 5 Kelvin?
Yep, Kelvin, like in the denominator, right?
Yeah, because -1.
All right. So now we could, what can we do with that?
Guess 1 second. So the first one is 2.0 times 10 to the negative 5 over Kelvin.
Huh?
We can we convert it to Celsius? Or,
So we could do that with here, but we would then multiply it, right? To get rid of the Kelvin
yeah,
denominator, right?
yeah.
Okay. And since it's plus or minus 2 centimeters, I think you may not need to convert it into Kelvin just because the
Yeah.
change
It's
in
small.
because the change in Celsius is still going to be equal to the change in Kelvin, right?
Hmm.
So yeah, you can try that. So I can start it out here. So for polymer one, we can have 2e negative 5 over Kelvin times 2, I'll just say Kelvin, would give me
4 times 10 to the negative 5.
so the Kelvins cancel. So this is going to be our new value, which we can take and turn into um, a percentage. Well, actually, uh, what am I missing here? Maintain its volume. So I have to connect this to volume. Um,
Shouldn't we be looking at this kind of?
Continuation coefficient. Maintain its volume. Um, okay, let's see if this works. All right, whatever. I'll just leave it like that for now, and then we can do. Attenuation coefficient millimeters on the bottom. Wonder if we do anything with that. What are your thoughts here?
I'm guessing like whatever's like left over is like plus or minus. Like I was putting these values over each other,
Uh-huh.
like zero point 0.2 over zero point 0.1.
Uh-huh.
It's me like 20.
Okay.
So I'm guessing maybe that maintained within plus or minus 0 0.0. I don't know. That's what I'm thinking.
Okay, maybe um the length could be this also. Both length of that. Okay. Um, okay, let's come back to this one.
Okay.
I'm not sure how to use like the attenuation. All right, so this is a question that we were kind of expecting, right? With them telling us
Yeah.
about the wavelength here and the diameter of the eye.
So it says what explains the fact that the ultrasound wave used for the emulsification of the opaque eye lens have a frequency of 30. Is that megahertz?
Yep.
Yeah. Okay. Use propagation of ultrasound waves, 15 ms.
So, what are your thoughts?
What we're talking about where the ultrasound waves are,
Mhm.
it was more to the right. So it
Um,
would have,
what's up? Oh, sorry.
so like when we're comparing the wavelengths, we said the ultrasound has higher energy. I
Oh,
know that.
that was for light,
Okay.
but yes, ultrasound means that it's at a higher frequency, right? And so we have what's mega mean? Like
10 to the 9. hertz
10 to the 6.
or 10 to the 6? Oh, giga is 10 to the 9. Okay, 10 to the 6.
Yep. So yeah. So so what are we given here and what can we do
So
with
we're
it?
given frequency, and then we're giving, it says provocation of ultrasound waves, meters per second. Is that just sound?
The speed of sound, uh-huh.
So, so I know that C is equal to F times wavelength, and we're given C and frequency. Oh, wait, yeah. Why don't you put 1500 over this?
So how did you set it up? Velocity is
I
equal to what?
put, I said wavelength equal to C over F,
Ooh, so be careful. C is used for what?
the speed of light.
What are we using it? Like what wave are we dealing with?
Ultrasound.
So that's
Wait.
sound, right? C is
Oh, yeah. So it's velocity.
uh-huh,
So it'd be velocity is equal to frequency times wavelength.
exactly.
And we're given frequency. So we're just going to do velocity over frequency is equal to wavelength.
Okay.
And then do the 1500 meters per second over 30 times 10 to the 6 hertz. We can convert the top one to scientific notation. So it'd be 15 times 10 to the 2 over 30 times 10 to the 6. And I'll get 2 minus 6. I'll get 0.5 times 10 to the negative 4. Uh, this is in meters.
Okay. Hmm. What do you end up with?
I'm stuck on the trying to convert it to centimeters or milliliters because I'm at 0.5 times 10 to the negative 4 meters.
You said
And
0.5
then,
times 10 to the negative 4 meters.
yeah,
Okay. And we're trying to convert it into?
uh, the like centimeters or milliliters.
Oh, well, which one would it be?
Milliliters because the wavelength. We're
Exactly,
not talking
right?
about amplitude.
Correct. Good.
Yeah,
So yeah, you could do so 1 e negative 3 meters is 1 millimeter, right?
millimeter. Mm-hmm.
So what do you do
So
in
it's one. So it'll
point
be
five?
-4 minus get -7.
So -4 minus -3.
Oh, sorry, minus -3. -1.
Okay.
Uh,
And then we can just move the decimal place to the left once to get 0.05 millimeters, right?
Yeah,
Okay.
and that's the wavelength.
Yep. So
So these are you. This says the energy is enough to emulsify the islands. That's wrong.
Yeah, because we don't know anything about, like, if it was light, we would know about the energy based on its
Mm-hmm.
frequency or wavelength. But if it's sound, so there's nothing that can help us figure out the energy of the sound here. Um,
Mm-hmm.
and then yeah, D is wrong because it can just have anything higher than that. So yeah, that's how you do
And
this
then
one.
okay.
Now, the previous question, I understand what, yeah, what happened.
Oh no. Okay.
So, oh yeah. So basically so we were doing it right, but it's just that, so I looked into the content outline that, shows all the stuff, all the content stuff, like, you know what I'm talking about in your spreadsheet. And I looked up linear expansion, and that comes up. So we have to know this. So this means that, um, so the for the volumetric expansion, its change in volume is equal to this beta term, which stands for the volumetric expansion coefficient, times delta
Mm-hmm.
T, and then times the volume. Now, um, now the so this is the volumetric expansion coefficient. Now we are given
Okay.
the coefficient of thermal expansion here as a linear expansion coefficient, right?
Mm-hmm.
And we can express that as alpha. So how do you go from linear to volume? You multiply by 3 because it's in 3 dimensions. So that's the math that we have to do. So if we did that, it would be for polymer A, 3 times 2 times 10 to the negative 5 times 2, which gives us 4. This gives us 12 e negative 5. Um, and then we have 3 times for polymer 2, 3 e negative 5 times 2. This gives us 9, 18 e negative 5. And then the next one is going to be 3 times the 4 e negative 5 times the 2. And this gives us 24 e negative 5. And then the last one is going to be 3 times 5 e negative 5 times the 2. And this gives us 30 e negative 5. So now we want to convert these into percentages, which means we multiply it by 1e2. So this will just turn into 12 e negative 3, and then 18 e negative 3, and then 24 e negative 3, and 30 e negative 3. And we need the volume to be within 0.02. And so, by the way, this means that this is 0.012%, right?
Yeah.
0.018%, etc. So these are already too high, right?
Yeah.
So we have this and this left, polymer 1 and polymer 2. Now, they both fulfill the requirement of maintaining its volume, but then I think that's what they mean about when they say it must also allow as much light as possible to pass through it.
So you'd have to get the higher value.
Yeah, or rather, the lower, so the attenuation coefficient is means that, well, when you attenuate something, you weaken it. So if the attenuation coefficient is high, it should allow less light to travel through.
Mhm.
So between polymers 1 and 2, uh the one with of the lower attenuation coefficient is going to be um allow the most light to pass through it.
Yeah.
Yep. So, write like a note or something
Yeah,
about
that's the
that.
linear expansion thing.
Yeah, so the B here is the volumetric expansion, and the A alpha here is the linear expansion. And to go from volumetric expansion or to go from linear expansion to volumetric, you simply multiply it by 3 because you're doing it in 3 dimensions.
Mm. So then where'd you get so I understand you got it 3 times all that, but then what about the two right here?
So that's from,
Oh, the temperature. Oh, okay, okay.
yep, yep.
Oh, okay, okay. I don't think I've ever seen a question like this, to be honest.
Yeah, yeah, me neither. That's why like I went to the content outline from the AMC. Um,
Yeah.
yeah, you know what I'm talking about? Like in
Yeah,
the
yeah, yeah, I know the whole thing they have, yeah.
Yeah, so yeah, I looked through that and I found that I for the CP content, coefficient of expansion physics, that is a topic. So,
Mm,
yep.
cool. What is the number of neutrons in the metalloid atom present in the compound and the polymers used for the manufacturing of AIOLs? Metalloid? Aren't these the metalloids?
Sorry. Show me again?
Uh, like right here?
Yep.
Okay, and it says, what is the number of neutrons? So these are atomic number is the protons. So plus,
What are your thoughts?
what, thinking it's uh, like 14,
Mm-hmm.
because atomic number. So if this one has 14 protons, then
Yep.
so and then electrons are 14.
Yep. So you took the atomic mass of 28 and you subtracted it by 14.
Yeah.
Yep. Good job.
What is the maximum magnitude of the work done by the focusing muscles on the AIOL? The force is constant, has a magnitude of 2 micronewtons, and points in the direction of the AIOL displacement. And our answer is in joules.
Yep. So the AOIL displacement is what?
Um, I don't really know like the formula. I forgot that.
I don't know. Uh, well, you said the work formula? You forgot?
No, the work is just force times distance.
Yep. So what would we use here for distance?
The diameter thing.
Well, that's diameter, right?
Yeah.
But they're saying, okay, so AIOL displacement means what? Means that the location of it moved, right?
Hmm.
So it moves by how much total?
How about like right here? The 5 milliliters?
Yep.
Okay.
Yeah. So you can try that out. I'm gonna have to go to my next person.
Yeah, that's
So
fine.
yeah. So you'll just need 150 for today, and I'll see you sometime next week.
Okay, sounds good.
And have a happy Thanksgiving.
Thank you, you too. Thank you.